everyone. My name is Shiyu Chang from the University of Illinois at Urbana-Champaign. Thank you very much for attending our talk on positive and labeled learning in streaming networks. This is a joint work with my friend, colleague, mentor, advisors in UIUC, Michigan State University, and Yahoo. I would like to give a special thanks to Jilan, Dave, and Yi, who either used to work in Yahoo or is currently working in Yahoo. They provide us tremendous help in terms of discussion and computational power. Without their help, this work is nearly possible. To start my talk, I would like to find some common characteristics amongst several very, very important data mining tasks. The first one is link predictions. So the task is given a set of networks, and we observe a bunch of connections between the nodes. You can think the networks is social networks like a Facebook. The link will be just the friendships. And the task is for us to predict whether two nodes gonna connect in near future. The second task is recommendation. You have a list of users and also a list of content or items. And you have the interaction between users and content, where in this regime really restrict us to the recommendation with implicit feedbacks, meaning the link could be either you listen to a music, you watched a TV show, or you purchased something, but you don't have any rating information or explicit rating things. So what we can see from these two applications, anything in common? So we observe the first thing in common is both of the tasks are naturally, the data are naturally can be represented as networks, right? So for the link prediction task, the task itself is just a network-oriented task, so no doubt. And for recommendation is really a bipartite network, right? With list of users and list of items on both sides. The second thing is there's no negative signal you observe from this data, meaning you only observe positive things. You and I connect, meaning we share something in common. But for those nodes never connect, you don't know because either they hate each other or they never met in this world. So that's what we call there's no negative signal can be observed from those data. Besides this two common things, any other common things? Yes. For any real-world system, you never observe data just like boom, you get a network. Instead, the network, the data is given in this way. You first observe two users. They have a link. New user introduced to your system. Observe another link, and then go on. So basically, all the data is formed kind of like a data stream, flow into your system continuously and consistently. And the second thing is, for all those data, when they arrive to your system, it naturally comes with the time. And this time is allow us to model users' preference changes, items' popularity changes, and all those are very, very important for any prediction tasks. So that's the four questions, four common characteristics we observe. And in this talk, we would like to answer a question. That is whether we can unify those applications with same characteristic to a single framework. If yes, how? So the answer is a positive one. Otherwise, I won't be here. And then before answering how to do it, I want first to tell you why there's only those common characteristics is very easy to observe, but why there's no such a thing before. This is because in order to do so, we're facing 3 challenges. First, because of the streaming nature for those data, it requires for any learning algorithm, any algorithms, to work on the one pass of the data. So meaning you never want to store this data and perform in a batch way. When data arrive, you want to catch the user instantaneous needs, so you require your model have to be performed in an online fashion. And also, you never can assume a fixed size of your data. You cannot just say, I assume there's like 100 nodes in your network, because that's not true for any real-world system. Like every second, there's always new user registered to a system. Second is the unlabeled negativities. How can we identify those negative signal from those unlabeled one in a principled way? That's another difficulty. The third thing is, how can we model the continuous time in order to incorporate the user's preference changes along the time? So in the following talk, I will answer the question how to unify those applications into a same framework by solving these 3 challenges simultaneously. So before to solve those questions, and I will first introduce the streaming network representations. So we specifically assume for a given network, there are 2 types of nodes, type 1 and type 2. So basically, for link prediction tasks, there's only one type. It's all users. But to make it work for link prediction as well, so we assume type 1 and type 2. You can assume there's one type for user, one type for item. And number of the nodes in the network in any given time t represent as mt and nt. The reason the size is time dependent because we want always incorporate the new nodes introduction into our model. And the interaction between 2 nodes is Lij at time t. And I want to emphasize one thing. What is the streaming PU setting versus the static one? This is very fundamental compared to our work to other existing work. So for 2 links, 2 nodes being linked to each other, we assume all those connections are instantaneous. Meaning, if you like something, you listen to a music, you like something, that only can represent your preference at the current time. It doesn't tell me any information or imply you will keep liking it in any future times. And this is very natural for the recommendation task, right? And somebody from the my poster section last night asked me whether that is reasonable for link prediction task. Because if we become friends in Facebook, we're always friends. I argue that it's still true because in most of the social network, there's impossible for us to canceling an edge. Or canceling edge, you have to pay a lot, right? So now we're a friend. You never want to say, I break the friendship on Facebook. You're going to pay a lot for that. And for co-author network, you never can break that link, right? But if I ask you the same question, like if we become friends 3 days ago, but if I ask you the same question right now, maybe you realize I'm a bad guy, so you don't want to be a friend with me anymore. So that's still true for link prediction tasks. So this is a graphical illustration demonstrate what I'm just said. For conventional setting, you get given a matrix, 2 users, A and B, like 3 items, C, D, E, and then you know 2 interactions there. However, we should unfold this thing along the temporal directions. If we do so, this is really should look like this. At the beginning of the world, you have 2 user, 2 item there. And then later on, user A engaged with item D. And then new item introduced to your system, and then B connects with E. So under this work, everything should be along the temporal direction, everything has to be ordered and be in a causal way. So because E introduced, B then can interact with D. So everything should be in a causal direction. So that is what we are working on, and that is the setting we're working on for this work. So, and the prediction task is for us is to predict whether a node pair gonna connect in near future given any time t. Formally, that means if Lij t equals 0 at right now, we want to predict Lij t plus. T plus means just little time in advance, whether it will become 1 or not. So formally, we want to minimize this probability, the error probability. In order to achieve this goal, we use a fully Bayesian approach. So in order to do so, I need to explain 2 parts. So first is how to model those probabilities, and the second one is I have to provide a trackable inference scheme so that we can do online updating. We can work on one pass of the data. So I give a graphical illustration of, about our probabilistic model. So this is temporal direction. At first time, you have an item, and then later on, a user comes, and then this is the temporal smoothness, and they connect, they interact at the t prime time. And then later on, another user introduced, and then they connect with the item 1. That is, although by first glance at it, it might confuse to you guys, but I will narrow it down and explain piece by piece. So first, let's zoom in this part. So the link between 2 nodes in a given network, we assume it's gonna affected by 2 terms, 2 factors. The first factor is the xijt, meaning the mutual interests between 2 nodes. So we assume 2 things being connected, they at least share something in common. Otherwise, it won't happen. The second thing is the OIJ, is what we call the observability. So meaning, if 2 nodes is not connected, it might either you don't like it, or because you never knowing the existence of that thing. So it's called the observability. So formally, we define Lij as the following form. So being connect, if and only if you observe that thing and you also like it. That's the only criteria you linked with that thing. And now, since I introduced O and X, now I have to give the probability assumption on them. So for observability, we specifically assume it depends on 2 factors. The first factor is the liveness of the network. So meaning, if the node in the network is actively seeking other nodes, it's easier for you to observe new nodes, other nodes, and the other factor is the cost of connections, meaning how much you have to pay in order to connect. Although this 2 factor is very hard, it's very abstract, very hard to model, we intuitively find liveness of the network is proportionally to the number of recent established links, while the cost is inversely proportional to the number of recent born nodes. Meaning, like say, if you have a network, every second there are hundreds of nodes introduced, And for you, the probability to knowing those things introduced to the network is low. That's what we call the cost of a connection. So the ratio of them, we call it the new link to new node ratio. And then we give the prior distribution on it. And then for the mutual interest, we think for each node has a hidden topic model. And then the probability for being like to each other is the inner product being as the mean of the Gaussian. And for the temporal smoothness, we use Brownian motion to adopt this temporal smoothness. And then we already observed, I already explained all the part of this graphical model. So I think we can properly write out the joint distribution now. And then now I have to jump into the inference part, how to correctly calculate this probability. So we use the MMSE estimates, which I will not have time to go into the detail, but I want to point out three things. For the inference scheme, we propose a recursive variational inference scheme, which is an alternative and a recursive way. And there's a three advantage, meaning if there's no events, no new things introduced to your system, you don't have to update anything. Your model only updates the node, like say if you and I connect, the model only have to update your model and my model for this time. Other irrelevant nodes don't have to update. And then all the updating formula is based on first and second order sufficient statistics, which is the mean and variance, and which we have a closed form solution, which is very efficient. And we validate our model by using 5 public available data sets, 2 link prediction data set, and 3 recommendation ones. And our setting, we adopt online testing scheme. We have a 30% of the validation set. And then for testing, we first set our reference time at the end of validation set, and then to do prediction. And then after prediction, we move our reference time one event time before, and treat that as the current time, and then do the prediction for the next time, and so on and so on. And we compare our algorithm with a set of baselines, and clearly show our model outperforms all of them. And we also validate the assumption of our prior distribution by, we assume a good prior will always give you a good result in terms of testing. So for both, ignore the black dot for now. We did a grid search for the parameter of this O factor. And then the more yellowish means the better performance. And then if we use our prior distribution for testing purpose, that's the black dot. You can clearly see it kind of follow the yellow belt, right? To give you kind of good performance using this with the defined prior distribution. And we also, this model is also able to distinguish positive, unlabeled, negative signal from those unlabeled ones. So what we did is at the current time, like we randomly sample a 3x3 part, it's all 0. And then in the next time, some of the entry will become to 1. And then along what we predict, and we can see the color is the probability of this pair, no pair, being equal to 1. That means the darker, the less the value is. Meaning for those entry is 1, the model tell me is not being observed. So basically it's hidden ones, which is validate our assumption. And this graph also show you the temporal smoothness, the hidden characteristic shift along the time. That basically concludes my talk. Thank you very much.
We have time for questions.
It's a very nice talk. I have a quick question. So in your problem, the network will have new nodes arriving over the time, right? It's just like, how did you predict whether I will like the movie if the movie has not existed yet? So how did you predict future links?
So, well, I cannot predict any future. So at the current time, I want to predict what's going to be happening in the future, right? What are you going to like? But if at the current time this item is not exist, I will never predict that one because I don't know what. Because everything have to be in a prospective way. If I don't, I cannot use any future information, so I won't predict that thing because I have no idea about what's going to happen in the future. Okay. Thank you.
Thank you. Very interesting. The question I'm wondering is how the counter approach captures the temporal or say the sequence ordering information. The sequence ordering information I mean here is as example, I first follow A, then I follow B. So from the streaming data, then actually it already indicates some prior information about it. I actually prefer A more than B.
Sure, of course. Because if you predict if you like some A first, the model will change based on your behavior, right? And then that will become as a prior information for your action in the next time, right? So of course, the model is already incorporated what you just described, I think.
But actually, because we converted this into the streaming graph, we didn't capture the previous ordering between the two items A and B.
Yes, so, you don't know so the observation is passed, but the knowledge, you have the memory from what you see before in terms of your hidden topics. But I won't see that observation anymore, but I still, basically that knowledge is already being encoded to your latent representations. I don't know if I explained well enough.
I think, thank you.
Thank you.
We've got time for one last question over there.
Hello. I know the price is very important for the base model, so I want to ask how the price affects your model and how to choose the price. Thank you.
So is the distribution or the parameter? You mean the form of the distribution or the parameter in the prior? So basically, I'm asking you're asking why is the Gaussian, or you're asking how to choose those sigma e's? Or let me answer you both. So,
thank you.
Briefly.
Okay, so in terms of why is the Gaussian distribution, I don't know. I don't know why. It's just my belief or everybody's belief. And in terms of how to choose the parameter, this is what we use for the validation set. So this is the basically. I also have this question last night. So for this model, we don't have the learning part. Everything is inference. So we don't learn the sigma e. So the sigma e is chosen from like expertise or from this validation set. If you want to learn that, that means you have to have an EM step involved into the model, which require both. So this model is purely a filtering process. So basically forward process. If you want to use EM to learn those sigmas, then you have to have a forward and a password pass in order to do a more correct estimate for any given time. I don't know.
Okay, thank you. You can take it offline.
All right, thanks.
That's all we've got time for. Let's thank the speaker again.